What follows is a tutorial on applications of triple integrals. By Jim Franklin. In each of the cases that we consider in this tutorial, we'll have a solid, let's call it S, in 3D space. So maybe it looks something like this. And what we're going to do is we're going to figure out triple integral formulas for finding various quantities associated with S. Things like its volume or its mass, first moments of S about various planes. We'll stick to moments about the coordinate planes actually, and second moments, that is moments of inertia about the coordinate axes. And then once we have formulas for the mass and the first moments, we can use the definition of center of mass to derive formulas for finding the actual coordinates of the center of mass. Now, what we're going to do in each of these cases is we're going to partition S into n rectangular subsolids of volume delta V. So here is, say, the ith rectangular subsolid. And the volume is delta V, which is delta X times delta Y times delta Z. Now, in each of these subsolids, we're going to pick what's called a sample point. Let's say that's our sample point for this typical ith subsolid right there. Call the sample point P sub I. And let's say it has coordinates A sub I, B sub I, and C sub I. And then what we'll do is we'll use basic formulas for finding volume and mass for rectangular solids that have constant density, and for finding first moments and second moments of point masses to find the typical piece of volume or typical piece of mass or typical piece of first or second moment of this typical rectangular subsolid by either treating it as a rectangular subsolid of constant density or by treating it as a point mass located at the point P sub I. Okay, let's call the quantity that we're trying to find Q. By treating the ith subsolid as either a rectangular subsolid of constant density or as a point mass located at point P sub I, we can find the typical piece of Q associated with the ith subsolid. Let's call that typical piece delta Q sub I. And then to get the total of the quantity Q, what we do is we add up these delta Q sub I's, and of course we sum as I goes from 1 to n. So we'll say that the total is approximately equal to the sum as I goes from 1 to n of delta Q sub I. And then we take the limit as n goes to infinity to get the actual value of Q. And what we have is a limit of Riemann sums, the limit as I goes from 1 to n, delta Q sub I, which of course is by definition in this 3D situation the triple integral over our solid S of dq, where dq is basically the typical piece of Q that we have by looking at the typical subsolid, typical rectangular subsolid piece of S. For instance, if the quantity Q we're trying to find is the total volume, then the total volume will be the triple integral over S, and then we need the typical piece of volume that occurs, which is delta V, which of course, after we take the limit of Riemann sums, becomes dV. So this is the triple integral that will give us the total volume of S, the triple integral over the solid S, dV. Now, suppose the density at xyz is delta of xyz. That gives the density, mass per unit volume, at xyz. Now, to find the total mass of S, in the argument up above where we took the limit of Riemann sums, Q is now the total mass, which will denote big M. And from what we did up above, we know we get the triple integral over S. And then our dq is dm, typical piece of mass. But since density is mass per unit volume, mass is density times volume. Remember, we're treating the typical rectangular subsolid as having uniform density. So the triple integral that we get is triple integral over S, density times volume, delta of xyz. Of course, when we say density times volume, we mean typical piece of density times volume, which is delta of xyz times dV. And we've got our formula for the mass. Now, suppose we want to address the moments of S about the coordinate planes. Well, the basic formula for the first moment of a point mass about a plane is that moment equals the mass times the displacement. So that's all we have to remember in order to derive our triple integral formulas for the moments about the coordinate planes. Well, let's denote the moment about the xy plane, big M sub xy. Well, from our limit of Riemann sum argument, we know that this is going to be a triple integral over S. And now next to the triple integral, we need to put a typical piece of first moment about the xy plane, which is typical piece of mass, delta of xyz times dV, times displacement from the xy plane, which is, for a point xyz, displacement from the xy plane is z. So z is our displacement, and then delta of xyz times dV is our mass, and we've got our formula for m sub xy. And similarly, m sub xz will be triple integral over S. That's mass times displacement, where displacement is displacement from the xz plane, which is y. So we have y times typical piece of mass, but typical piece of mass is density at xyz times dV. And then finally, we get m sub yz is equal to the triple integral over S. Let's see, displacement from the yz plane is x, so we have x, and then times delta of xyz dV. So we have our formulas for the first moments about the coordinate planes. Now, for the moments of inertia, about the coordinate axes, we need to use the definition that moment of inertia of a point mass about an axis is mass times displacement squared. So all we really have to remember here is that we want mass times displacement squared. Now let's denote the moment, the second moment, the moment of inertia about the x-axis, I sub x. Well, it's going to be one of our triple integrals, and it's over our solid S. But now, next to the integral sign, we need mass times displacement squared. Now, displacement from point x, y, z to the x-axis in 3D space is square root of y squared plus z squared. But we need that squared. So we get y squared plus z squared as our displacement squared, and then times our mass, typical piece of mass, which is delta of x, y, z times dv. And then similarly, I sub y is triple integral over s. So we need mass times displacement squared, but now displacement squared is x squared plus z squared. And then typical piece of mass is delta of x, y, z dv. And I think I'll leave it to you to derive the formula for I sub z. We'll leave that as an exercise for the student. Now, in order to find the center of mass, we use the definition of center of mass as being the point x bar, y bar, z bar, such that the solid S acts as if it's a point mass of mass big M, same big M we found with the triple integral for the total mass earlier, concentrated at x bar, y bar, z bar. Well, using that fact, we can say that m sub xy is mass times displacement, so that would be our mass, big M, times displacement from the xy plane, but remember, we're treating this as being concentrated at x bar, y bar, z bar, so the displacement is z bar. And the first moment about the yz plane would be the total mass, big M, times x bar, because remember, we're treating this mass, this solid, as being concentrated at x bar, y bar, z bar. And then the first moment about the xz plane is going to be big M times y bar. And that's times y bar, not sub y bar. Okay, from these three equations, we can get our formulas for the center of mass. The center of mass is the point x bar, y bar, z bar, where x bar is equal to m sub yz over m, and y bar is m sub xz over m, and z bar is m sub xy over m. Okay, let's look at some examples. Let's take our first example to be a where we have a solid, a rectangular solid, call it R, and it'll be the set of all points x, y, z in 3D space, where x ranges from negative a to a, y ranges from negative b to b, and z ranges from negative c to c. And let's write down the formulas for some of the quantities associated with R. First, let's write down the volume formula. You know, that's just the triple integral over R dV. Let's go ahead and write the iterated integral for this triple integral. This would be integral. The order of integration is your choice here, but obviously rectangular coordinates is the way to go. So if we go dz dy dx, then z will go from negative c to c, y will go from negative b to b, and x will go from negative a to a. Now, of course, these limits will be the same on the rest of the iterated integrals that we get in this example, because in each of those integrals we're talking about the same solid. Okay, suppose we want the mass. I call that big M. We know that's just triple integral over R. And then next to the triple integral signs, we need a typical piece of mass, which is density times volume. Now, since I neglected to tell you what the density was, let's just assume we have a density function, delta of x, y, z. And that's going to be your mass. And, of course, the iterated integral would look like the iterated integral up above, except you would have a delta of x, y, z as your integrand instead of just a 1. Okay, now let's write the moment about the xy plane. That's going to be the triple integral over your solid. Okay, we need mass times displacement, so that's just going to be z times your delta of x, y, z dV. And then if we were to take m sub x, y over m, that would give us the z coordinate of the center of mass, the z bar. Now let's consider the moment of inertia about the z-axis for this situation, and let's suppose that the density is constant. Just call it delta instead of delta of x, y, z. Let's actually set up the iterated integral for that moment of inertia and have you evaluate it on your own. So I think I said we were going to find I sub z. So let's write I sub z. Okay, equals. And then we want the triple integral over our solid R. Okay, I remember moment of inertia, the basic formula is being mass times displacement squared. Well, displacement squared from the z-axis is x squared plus y squared. So we have x squared plus y squared. Our density is just delta. We need that times dV to give us our typical piece of mass. Density is mass per unit volume, so mass is density times volume. Now let's go ahead and write the iterated integral and then have you all evaluate it on your own for fun. Now the delta is constant, so you can bring it outside, and then you have your x squared plus y squared on the inside. And then for your dV, you've got 6 different orders that you can write. But let's say we do dz, dy, and dx. Then z is going to go from negative c to c, y will go from negative b to b, and x will go from negative a to a. Now, in your evaluation of this integral, you might be able to make your job easier by using the fact that, from Calculus 1, that if you integrate an even function from negative d to d, you can do it by going from 0 to d and then multiplying by 2. So it makes your limits of integration nicer. Anyway, give it a try. For our second example, let's consider the right circular cylinder pictured. It's going to have radius big R and height big H, base in the xy plane, centered around the z-axis. The picture will say it better than I can. And the radius is big R, so this point here would be 0, big R 0, and the height is big H, so this point here would be 0, big R, big H. And let's go ahead and write the triple integral for the moment of inertia about the z-axis, and also write the iterated integral that we would use to evaluate the triple integral. Okay, the moment of inertia about the z-axis is, of course, triple integral over our cylinder. Let's call it z. Let's suppose that it has constant density delta. Okay. Now, the moment of inertia about the z-axis is triple integral over our solid, and that's, I remember, it's mass times displacement squared. Okay, and we have displacement squared from the z-axis as being x squared plus y squared. And I need my mass, which is delta dv. Okay, so there's the triple integral that will give me the moment of inertia about the z-axis. Triple integral, mass times displacement squared. Now, obviously, the best way to evaluate this triple integral would be with polar coordinates, which you remember as being r, theta, and z, where z is z and r and theta are the polar coordinates from the xy plane. So writing the iterated integral in polar form, let's see, x squared plus y squared is r squared. So there's the r squared. Again, the delta can be brought outside. And then dv in cylindrical form is dz dA, but dA is r dr d theta. Okay, and then on the innermost integral, when we integrate with respect to z, obviously z goes from 0 to h. And then when we go down into the xy plane to integrate over the disk centered at the origin with the radius big R, little r goes from 0 to big R, as theta goes from 0 to 2 pi. And then we evaluate that iterated integral, and we'll have the moment of inertia about the z-axis. And after you do it, you can get your physics book out or Google moment of inertia of a right circular cylinder and see if you did the problem correctly. Because you'll be able to look up the formula for the moment of inertia. Now, as a final example, let's consider the sphere of radius r, radius big R, centered at the origin. So here's your sphere. Radius big R centered at the origin. So let's see, this point here would be 0, R, 0. Okay, now let's find the moment of inertia of this sphere about the z-axis. In other words, let's find I sub z. And again, let's assume that delta is constant, the density is constant. So the density is constant, value delta. Now obviously, the way to go here is going to be spherical coordinates. First, let's write the triple integral that will give us I sub z. That's easy. Writing the triple integral is easy. We have triple integral over the sphere, let's call it S, and then mass times displacement squared. That's just going to be x squared plus y squared, delta dv. Now, when you convert this to spherical coordinates, remembering the relationships between x, y, z, rho, phi, and theta, we know that, first of all, x is our cosine theta, y is our sine theta, or better yet, we can remember that x squared plus y squared is r squared, but then r is rho sine phi. So x squared plus y squared can be written as rho squared sine squared phi. But then remember, your dv in spherical form is rho squared sine phi d rho d phi d theta. So it looks like you're going to get a fairly messy integral if you do this. And what's interesting about this problem is if you use the fact that the moments of inertia about the x-axis, y-axis, and z-axis are all the same, then you can add those up. And that's the same thing as getting 3 times I sub z. So if we multiply this sum by 1/3, that will give us I sub z. But when we add these 3 integrals, if you look at I sub z, it's triple integral over s, x squared plus y squared delta dv. Then I sub x, instead of having x squared plus y squared, we'll have y squared plus z squared. And I sub y will have x squared plus z squared. And if we add those 3 integrals, we get that I sub z is 1/3. And then adding the 3 integrals, of course, the delta can be pulled outside. So we have 1/3 delta. And then times the triple integral over s. But then adding all the sums of squares, we get a 2x squared plus 2y squared plus 2z squared. The 2 can come outside. X squared plus y squared plus z squared is rho squared. And then we have our dv, which is rho squared sine phi d rho d phi d theta. Anyway, I know I didn't supply a whole lot of detail in writing here on this, so you need to go home or sit where you are now and think about this, fill in all the little missing pieces, and figuring out where I got this final form of I sub z. But at any rate, you see that the integral is going to be pretty easy to evaluate. Let me go ahead and instead of writing triple integral over s, let me go ahead and get rid of the s here and put the limits on what we'd have as an iterated integral. Rho would go from 0 to r, and phi would go from 0 to pi, and theta would go from 0 to 2 pi. That's it.